Hi, it is me, Jirke, founder of Step School, and today we will start a very significant topic in STM32 programming, which is designing a custom bootloader. So whether you are a professional or hobbyist in STM32 programming, knowing how to design a custom bootloader will help you to do many cool things. Also in professional embedded programming, in the program in embedded in the product development, having a custom bootloader is a must-have feature. So why do we need a bootloader? So imagine that you design and the best smartwatch in the world. So you already delivered your product to thousands of customers. They're using it, and at some point you find out that there's a bug in your application. Also, there's some feature you want to implement. So in that case, you cannot ask you every customer, oh, please bring your smartwatch. I will open it and I will flash the new firmware using the ST-Link. Of course, it is not going to work. But what is a feasible approach is to have a smartphone connected to your smartwatch. Then you have an application running, and when you develop a new version of the firmware, you send the binary file to the application running on the smartphone. Then it will send the commands to the smartwatch saying, oh, there's a new application, new firmware version. Then you wirelessly send the binary file to the smartwatch. Then it will update the firmware, fixing the bugs and adding new feature to your product. So this is how probably your smartwatch is going to modify its own firmware. So in other words, when you design a product or robot, the application, like the code running in your product, should always have an ability to update itself by receiving a binary file through some interface. It could be wireless, for example, Bluetooth, or it could be USB, UART, and etc. So in this series of videos, we will learn how to design our custom bootloader, and we are going to cover the following topics. So first, we talk about the bootloader itself, and then we talk about CRC, cyclic redundancy check, to detect errors, and we will implement it within the STM32 microcontroller. Also, we will talk about how to implement UART in DMA mode. Also, we develop a Python program to send our binary file to our microcontroller. And finally, we will implement dual boot mode. So you are going to learn a lot of things in this tutorial. So please don't forget to subscribe and not to miss new videos of the tutorial, and please press the like button so I can reach other people who are interested in embedded programming and STM32 programming and robotics. So let's move on and let's talk about the bootloader. So what is a bootloader? Bootloader is a piece of software to load the main program. And usually a vendor provides a bootloader along with the device. So for example, if you buy a completely new computer without the operating system, you can still press the power button. It will start operating. So the bootloader will try to find the operating system. And if it fails, it will show a message on your screen. So meaning that the bootloader is necessary to load the main program. And you can consider it as domino tiles. So you need to knock down the first one so the rest will fall down. In a similar way, bootloader will initialize the stack pointer, it will initialize the program counter, other things, then it will give a lead to the main program. And usually we can configure the bootloader, how it works, but we cannot completely change it. So in our case, what we are going to do, we are going to build something on top of the bootloader we have inside the microcontroller. And before introducing how we can do that, I want to first, of course, introduce the flash memory. Flash memory is a non-volatile memory chip which is nowadays widely used in embedded systems. Non-volatile means is that even if you power off your device, your microcontroller, you will not lose the data. So you power off and you still have the data inside. But for example, if you have volatile memory chip, for example RAM, you power off and everything is lost. So that's why we use flash memory to store the program, application program. So for example, we have the project, we compile it. Once we compile it, we have the binary file, and all this binary file will be sent to the microcontroller, for example, through the ST-Link. And what would happen is that we this application program, the binary file will be stored inside this flash memory. And when we turn on the device, the bootloader will start running, will initialize the program counter to the memory address of the flash memory. So the program inside the flash memory will start working. And I took this figure from the reference manual of the STM32 L4 microcontroller. So this figure shows the organization of the flash module. So as you see, we have pages, page 0, page 1, 2, 3, up to 511. And we have two banks, bank 1 and bank 2. And later I will explain why we have these bank 1 and bank 2. And next, let me show this picture, which illustrates how we can design the bootloader. So usually we have the application program, which is the main program running inside the microcontroller. It could be, let's say, your smartwatch, or it could be, let's say, robot operating. And usually we send some command to your application, or it could be like pressing specific button on your device, or it could be sending some command. And then what would happen is that the program, the microcontroller, will jump to another application, which is a bootloader. So the bootloader will run, and we will send the binary file through some interface. It could be UART, or it could be, let's say, wireless. Then the bootloader will update this application code, and once it finishes, it will go back to the application. So this way we can update the application. And when it comes to the flash memory, for this bootloader, we usually devote a couple of, let's say, pages, and the rest is for the application. So we can basically store two programs, two applications at the same time, but of course they will not run in parallel. Only one application can run at a time. But in this tutorial, we are going to implement this approach. So basically, instead of having just a single application, we will have two versions of the application running. So we have application 1 and application 2, and both applications can update each other. So if we are running application 1, we can still send the binary file and it will update the application 2, and in a similar way application 2 can update the application 1. And as an interface we will use UART of the STM32 microcontroller. And one of the advantages of this method is that if new version is not working well, we can still restore the old version. So for example, you update, you have the new version running in application 2, and if something is not going well, we can go back to application 1. So this way we can still we can keep two versions of the same application. So we are going to implement this approach. So at this point, some ideas might seem too abstract for you, but don't worry, because right now we will dive into the details of implementing this approach. So here, instead of interface, as I said, we will use UART communication. And right now I'm going to explain how I configured UART. So on my project, of course, I will use the CubeMx file to configure UART. And I already created the project, I configured it, so I skipped this part. But of course, if you want to know the details, the essentials of STM32 programming, you can refer to my introductory course, STM32 introductory course on my website, where you would learn how to use STM32 CubeID, you will learn interrupts, timers, UART, bare metal programming, and other topics. And you can find the link in the description below. So let's go back to our project, our tutorial. So I have UART2. I enabled it by choosing asynchronous mode, and the parameter settings, everything is default. So I have the baud rate, word length, and also I enabled the UART for receiving and for transmitting. And here everything is the default parameter settings. And within the NVEC settings, of course, we have to enable the interrupts. So we have the UART ready, but there's another thing we need to talk, which is cyclic redundancy check. When transmitting the binary file, we have to be 100% sure that the data is not corrupted. So if we have some accidental changes, our program is not going to work. And that's why we will use cyclic redundancy check, CRC, to detect accidental changes. So when using SRC, we compute a check value for the data. So we have some buffer. So we compute the check value. And when we send the data, we also send this check value. And when the microcontroller receives the data, it will compute the check value again, but for the received data. And if these two check values match each other, the received and the one which is computed, then we can be sure that we don't have any accidental changes, that our data is reliable. So, and of course, on the web, there are plenty of materials about SIC, so I'm going to skip this part and we will immediately jump to the implementation of it within the STM32 microcontroller. So in our project, in our CubeMx file, we go to computing, we go to SRC, and we just activate it. And here for input data format, we choose words. That's it. After this, you can save the file, or you can press this button to generate the code. So we have UART and the SRC initialized, and to receive data from the computer, I usually use this function receive to idle using a direct memory access. So why I'm using this function? because usually when we use UART, we specify the number of bytes we expect. So it could be, let's say, 10, 20, 30. And the hard thing is that even if we specify 10, but if we actually receive 15, we lose these 5 bytes. So if we have packets with the varying size, it is hard to use the UART to and not to lose data. That's why I use this function, receive to idle, so it will keep receiving data until we have the idle state. So this way we can receive packets with the varying size. And when using this function, we still need to specify the size, but this is the maximum we expect. So I set this value very high value, so I will never achieve that, meaning that I always receive the whole packet. And when I receive data, I have this callback function invoked, and here, so when we have this callback function, this buffer holds the received data, and I have another variable UART size. I set its value to the number of bytes we received. So next thing, let me explain SRC. So when we receive our packet, this our data is stored inside this received data buffer, and we have this size. And within the while loop, I always check the value of this variable. So if UART size is not equal to 0, meaning that if we receive the data, I call this function verify SRC. So it has 4 arguments. So first is data, second is the length, number of bytes we received, and the host CRC, meaning that the value of CRC computed by the host. So here what I do when I call, of course, the pointer is received data, the buffer, and the size is UART size, the number of bytes we received, minus 4. And can you tell me why I'm subtracting 4? The answer is obvious, and I hope you find the answer, because the last 4 bytes is for SRC. So I have the whole data, and I add 4 bytes for SRC. So that's why I subtract 4. And to get the SRC, I'm just pointing to the last 4 bytes of the received data. So every time when we send data from the computer, we have the data, and the last 4 bytes is SRC. So all these arguments are pretty clear. And I use for loop, so I have the every data. Then I call this SRC accumulate, and this SRC is basically SRC handler, which is defined in our main function within the main file. So if we look SRC initialization, we have HCRC. So here I'm referring to the same handler. So here I just the second is the data pointer, and we have just 1 byte. And once we compute SRC, we have to reset SRC for the next use. And here I check if they equal, I return 0. If not, something is wrong, I return 1. If we go back to our main function, so I check SRC. If they're not equal, this function will return 1, and I will print SRC is wrong. Otherwise, I print the message SRC is matching each other, and I print the received data as a string. And for implementing printf, I will use a serial Y viewer, And of course, there is a video on my YouTube channel about implementing this function within the STM32 microcontroller. Next thing, let's look at my Python script. So in Python, you have a module called PySerial. So it's a very standard, so you can easily install it. Pip install PySerial. Then you can import it by calling import serial. And here I define the comport number. So when you connect to your microcontroller to the computer, you have a device manager. From that, you can find the comport number. And here I call serial, and here you need to define the comport number, the baud rate, the timeout. So I have these values, and I have this message, ukulele, something like this. And then I convert it to bytes, and I have this while loop. And right now you can ignore these messages. It's just I will explain them later. This is for boot update, but right now I want to show only UART application. Okay, right now you can forget about the bootloader. So if I type 1 on the console, I send this message to the microcontroller by calling this function. And I'm going to show how this function is implemented, send data serial. So send data serial, what I do here, I have another function, compute SRC, and I'm going to explain that right now. So here we have this compute SRC, which is necessary to compute SRC before sending it. So here I initialize this value to this, and we have this simple operation within the for loop. And then I do end operation. So you can just copy it. Or you can look on the web and you can find the implementation of this function. So basically this function returns CRC value for the input buffer. So when sending the data to the microcontroller, so by calling write function, I just add this SRC as unsigned integer number using this struct pack. So basically data holds data, actual data, plus these 4 bytes of SRC. So that's it. And right now we're going to check how all this works. Finally, we are ready to check our UART and the SRC. So first I want to verify that I have the comport 10. So if I open my device manager, as you see, we have comport 10. And then I have everything right here. This I'm going to explain later. So I'm going to flash by pressing the debug button. So right now I'm in the debugger perspective. I open data console and I run the application. Then I go back to my Python script. I run the script. Then I just enter 1 and let's see what is going to happen. So I've sent, and if I check my microcontroller, we have these messages printed. SRCs match each other and messages ukulele. So everything is working really well, and we can try again. Press 1. Again, I have the same message. Let me check again. Okay, everything is working. So if we send our binary file, we can be sure that data is not corrupted by checking the SRC value. So that's it for this lesson. Next thing, we will talk about flash memory, how we can update the flash memory, how we can run 2 applications at the same time. So hopefully we can finish this bootloader in the next video. And the source code I used in this project on this tutorial and this document you can find by joining my Patreon community. So once you join, you get all the materials and projects I worked so far in the STEP school. So thanks for watching, and hopefully see you soon. And please don't forget to press the like button. And if you have any questions, you can write the comments below. So bye.